Swayam Prabha. Digital India. Educated India.
Okay. So we are moving on now. So we're going to look at the PCY algorithm. This is a slight improvement over a priori, right? So, but this is still potentially a multi-pass algorithm, right? So we've been trying to see if we can improve on it, but it's still a multi-pass algorithm, right? So the key observation that we start off with is that in pass 1 of a priori, if you remember the memory pictures that we were showing you, right? In pass 1, most of the memory is free, right. So now we want to see if there is a way that we can somehow use this available main memory to reduce the number of pairs that we count, right. Remember what we do here, we basically have generated L1, right, and our C2 which we are counting now in pass 2 of a priori is literally pairs of all L2, right. So, it's n choose 2 in the L1, right, it is n choose 2 in L1. So, it is quite likely that two items that are frequent individually, right, when they are taken together they are not frequent. In fact, a good fraction of those candidate pairs are not going to be frequent. So, is there a way to identify this in the beginning itself, right, while we are doing pass 1. So, that is basically what these guys are doing in the PCY algorithm. So, can we reduce the memory required in pass 2, right. So, what we do, so in pass 1 is that, so apart from the item counts that we have building, we maintain a hash table, right, as large a hash table as can fit into the memory, right. And keep a count for each bucket, right, in this hash table, count how many times a pair of elements hash to that bucket. So, you have some hash function that takes a pair of elements and puts it into that bucket. So, just keep a count of the number of times, right, a pair of elements hashed into a bucket, right. So, you do not really need the actual elements that hash there, you just need the count for that bucket, right. So, this is basically what we are doing here, right. The first, this is pass 1, right. So, add each item, for each item in the basket you add 1 to the item's count. So, that is what we keep track in the top half of the top part of the memory, and for each pair of item hash the pair to a bucket, right, add 1 to the count for that bucket, right. So, we need to have some efficient way of generating these pairs, because the pairs are not present in the file, right. In the file you just have the list of items. So, from whatever you read, so maybe, or if you are reading it transaction at a time, right, then you have to make sure you generate all the pairs that are there in the transaction on the fly, and then you hash those pairs into the bucket, right. So, what we are really looking for now is to see that for every pair, is it possible that the pair has sufficient support, right. So, the idea is if a pair of items hash to a bucket, and if the bucket has appeared at least s times, right, then it is likely that the pair of items can have a count larger than s, or count larger than s. If it hashes to a bucket which has a count below s, right, at the end of it, then for sure it is not going to be a frequent item, frequent pair of items, right. So, that is basically the idea, right. So, if a frequent pair of item hashes to a bucket, then that bucket will be frequent, because every time you encounter that pair you will add 1 to the bucket. So, the bucket will be frequent. There might be other things, suppose the count is say 100 for this pair of frequent or rather frequent pair of items, the count is 100, right. The bucket might end up having a count of 300, because of lot of other items that are hashing to the same bucket, right. But the problem is, this is not the only condition when it is frequent. Suppose there are like 300 items, none of which are frequent, all of them happen to hash to the same bucket, and you across all of these you add up their counts, it might end up going above the threshold, right. So the bucket will end up being a frequent bucket, while none of the items that individually hash to that bucket will be frequent. That makes sense? So that can happen, right. But so that's one problem, right. So you will get frequent buckets which contain infrequent items, but if a bucket is infrequent, it is not frequent, then nothing that hashes to the bucket can be frequent, and therefore all those pairs can be eliminated. You do not have to count any of those pairs, okay. So what you do in pass 2 is that you only count pairs that hash to frequent buckets. You can still do the original filtering that you are doing in a priori. What was the original filtering you do in a priori? You count a pair only if both the elements are frequent. So you will have that filter still, okay, both elements have to be frequent and the pair has to hash to a frequent bucket. So that way you will not be counting all the items, pairs of items where one of them is not frequent just because it hashes to a frequent bucket, right. So I am just going to skip ahead very quickly to show you this slide, and I will come back and talk about what we have to do. So this is pass 1, right. So we did the item counts, and whatever space was left, we had this hash table, right. And then in pass 2, right, what do I need to do in pass 2? I need to know which pairs of elements hash to a frequent bucket, right. So I need to have some representation of the count in the hash table, because without access to the count I will not know which pairs were frequent, right. So what I do here is I have a way of summarizing this hash table into a bitmap, right. So now I have my original set of frequent items, I have a bitmap that tells me about this hash table, and then I count the candidate pairs, okay. So how do I do this, right. So I replace this set of buckets, the hash table that I had, I replace that with a bit vector, right. So 1 in a position means that the corresponding bucket had a count greater than S, right. 0 means it did not. I do not need to know what was the actual count, I just need to know whether it was above the threshold or below the threshold, right. If the bucket count exceeded the support, right, then I will put a 1 in the bit. If it did not exceed the support, I will put a 0 in the bit. So now I have a bit vector now, right. So the 4 byte integer counts are replaced by bit. So the bit vector requires really only 1/32 of the memory, right. So which are all the ij pairs that I will count now? So count all pairs ij that meet the condition for being a candidate pair, right. Both I and j are frequent items, and the pair ij hashes to a bucket whose bit is set to 1, right. So that is basically what we have here. So from the item counts I will get to the frequent items that I know, and the candidate pairs are those which satisfy these two conditions. So I have significantly reduced my L2 set, hopefully, by doing this, right. You can do more efficiency. So what is it that we are talking about here? Yeah, this one, right. So what does this hash table do? For each pair of elements it has a bucket, and the bucket has to hold a count, right. I said you need 4 bytes for the count, right. That means that for every bucket you are going to need 4 bytes. So that kind of limits the number of buckets that you can have in memory, right. Therefore, if the number of buckets becomes smaller, then there is more chance of collisions happening, right. And if you have more collisions happening, what is the problem? You have more chance that buckets will become frequent even without a truly frequent pair mapping to that bucket. So that is a problem, right. So one thing that we can think about is you look at what is your frequency threshold, right. It is a much smaller number, right. So you might not need 4 bytes to count for your frequency threshold, right. If your frequency threshold is say 10,000, how many bytes do you need? Too hard. 1,000, how many bytes do you need? One byte. You can go to 1024, right? No? 2 bytes. 3. Come on, guys. How many of you are non-CS people? 1, 3, 5. So many. Okay. You have an excuse. Put your hands down. The rest of you. If I have to represent a count of 1,000, how many bytes do I need? Okay. Okay, if I have only 1 byte, what is the largest count I can represent? 2 power 8. Okay. 1 byte. One byte I can represent 1023. $255. So if I want to represent 1,000, I can do a count 0 to 255, right. So if I want to do a count of 1,000 elements, I need 2 bytes. No, 1. 2 bytes. My God. Anyway, so small numbers, I don't need the 4 bytes that I need for the full integer representation, right. So if I cut it down to 2 bytes, then I can basically double the number of buckets that I use. Why is 2 bytes enough? Why the threshold is enough? Because I am not interested in how much I exceed the threshold by, I am only interested in if I reach the threshold or not, right. In fact, I can stop counting if a bucket reaches the threshold, and I will still have to hash, and if I hash it into a bucket that is already frequent, then I can stop counting. So therefore, I can reduce the amount of main memory that I use, right. Right, I went past too quickly. Yeah, right. I can reduce the number of main memory I use for per bucket by using fewer bytes than the full integer bytes, right. Okay. Here is another question for you guys. On the second pass, I need to use a table of item count, right. I have to use the sparse matrix representation. I can't use the triangular matrix representation. Why? Sorry?
Now along with frequent items, your buckets too.
Frequent items are still pairs of items, right. See, the thing with this matrix representation is that you really are counting items cross items, right. That is basically what you were counting earlier, right. So all the items that were frequent versus all the items that were frequent, because your candidate set was the frequent items cross frequent items. But now what you have done is you have taken this and you have done a further filtering to throw away a lot of candidate pairs, right. If they do not hash to a frequent bucket, you throw them away, right. So now even if I do a matrix representation, a lot of those entries will never be used, but I will still be creating memory for them, right. And therefore, right. So we do not want to use the triangular matrix approach. So we have to use this item count, right. And also these item can be all over the place, right. Some items might appear many times as in parts of various pairs. Some items might not appear at all. Maybe they will appear just once in a frequent pair, right. We do not want to waste memory by allotting that, right. So we need to basically then make sure that at least 2/3 of the candidate pairs are eliminated by PCY, so that we beat a priori in terms of memory requirements. Otherwise, we will end up requiring more memory than. So, remember we started doing this saying that hey, we will try to reduce the memory required in pass 2, right, but we might end up taking up more memory in pass 2 unless 2/3 of the candidate pairs are eliminated, right. So, if you remember, we started doing all of this thing because we said memory is a bottleneck, right, that we are not able to keep track of a large number of pairs, right, we try to reduce the number of pairs. So, in this particular approach, we are going to trade off the number of passes that we do versus the peak memory requirement that we are going to have, right, we are going to trade off the number of passes that we do versus the peak memory requirement. So, what did we do in the PCY algorithm? We first, in the first pass, we tried to keep track of frequent pairs, right. But what was happening in the PCY algorithm is whether I and j were frequent or not, right, whether a pair is already there in C2 according to the a priori algorithm or not, I was hashing it into a bucket, right. See, this bucket hashing happened in pass 1, right, that means that I do not have the counts of the individual items yet, I do not have the count of the individual item. So, if I generate a pair I comma j here, I do not know whether I and j are both individually frequent, right, but still I will generate that pair and then I will hash it into a bucket, right. So, it will contribute to the count in the bucket. So, there, well, I and j both are not frequent, therefore, they would have never come into my second stage processing, but what they will do is artificially inflate the count of a bucket, right, but I had no way of filtering it in pass 1, right. So, that is one of the reasons you get a lot of false frequent buckets, false positive buckets in end of phase 1 in PCY algorithm, because a lot of potentially for sure not frequent candidates also contribute to the counts of the buckets, okay. So, we can now make a 2 pass algorithm, right. So, what we do, the pass 1, right, so we have done this, right, we have done the filtering according to pass 1. Now, I have my candidate frequent sets that I am going to count in pass 2 of PCY, right. Now, what I do is I do not actually count them. So, instead of counting them, I do the same hash trick again. I take each pair of items that have passed through from PCY, right, these set of items, right. These are the candidate pairs that come to pass 2, right, for PCY algorithm. So, I will take those candidate pairs, right, I will again hash them, right. Remember the candidate pair condition, I and j both are individually frequent and ij hashes to a frequent bucket from pass 1, right. Now, there are lot fewer candidates for me to hash and therefore, lot fewer false contributors to the buckets. Then I go and do the actual counting in the third pass. So, this is basically what I do. Right. So, I do the item counts initially at the first hash table, counts pairs ij, whether I and j are frequent or not, but it counts hash pairs ij. So, you will get a lot of frequent buckets, right. So, in the second phase you take all the individually frequent items here, right, and then the bitmap that we constructed from the first time around, right, and then if the 2 items are frequent and the pair hashes to a frequent bitmap, then you hash it again into the second table and count the bucket there, right. This 2-step stage process clear. So, I will pick 2 items from here, right, I will pick 2 items from here, I will check whether these two items hash to a 1. Okay, if these two items the pair hashes to a 1, then I will rehash it to some bucket here and add a 1 to the count. Okay, just like I did in phase 1 or pass 1, I will do the same thing in pass 2, but now I will only count if they are frequent, if they are already belonging to the candidate set. Then what I do in pass 3, I go back and condense this into forming a second bitmap, right. Again I have the same frequent table that has come here. Now what I will do, I will pick a pair here ij from two frequent items here, right, check if it hashes to a frequent item here, check if it hashes to a frequent bin here, both I check, and if all the three conditions are true, then I actually count that, right. So I will basically have a count of I j count. That entry will go into my count table, actual count table. Okay. So here is a question for you. Do people understand the whole process now? It's become pretty complicated. Just to count pairs, I have done a 3-pass algorithm, right? But we have been very stringent. So in my C2 has been pruned significantly by the time I come to pass 3, right? Then of course I will count from here, and then finally I will get a L2 as my output, which is the truly frequent pairs. Okay. So if you truly understood what is going on, tell me why do I have to check whether this item is in bitmap 1 it is frequent and in bitmap 2 it is frequent. Why can't I directly check whether it is frequent in bitmap 2? I could, right? Right. So what we did here, we only elements that were frequent in bitmap 1, we hashed them into a bin here and counted the number of occurrences, right. So why can't I just take this ij, see if it is a 1 in bitmap 2, and then if it is a 1 count? Why do I have to check whether it is a 1 in bitmap 1 also? Not needed, we can remove that part of the algorithm. Yeah, you're on the verge of saying something, say it. You actually opened your mouth and closed it twice.
Irrespective, when we add I and J, whether they are existing frequently, individually or not, we are hashing them. And then
That's here.
if and only if they are frequent, we are adding to a frequent bucket, which is V1.
Yeah.
So here we are trying to prune it that it will be at most frequent item, and that is how it is, we are using going through this.
No,
The end result.
no, the question is something else, right? The question I am asking you is, so here I took ij, they were both frequent, I found out whether the pair ij hashes to a frequent bucket, and if it did, then I rehashed it to another bin and I counted it, right, and this second hash table has been contracted into that bitmap. So now I am saying when I want to find out the true candidate pairs, right, so I will take the pair ij, first hash it to bitmap 1, see if it is a 1, then hash it to bitmap 2, see if it is a 1. If it is 1 in both the bitmaps, only then I will take it as a candidate pair, right. So my question is, already we will only put an entry into bitmap 2 if it has a 1 in bitmap 1, right. In pass 3, why do I have to check again whether it is a 1 in bitmap 1? Why can't I just directly check if it is a 1 in bitmap 2, which means it is frequent according to the second count I made, then just go ahead with it. Why do I have to check in both bitmaps?
Check for the next triples. Like it is only
It is not triple, I am just doing only doubles still, I am only counting pairs still.
when we are going from the second hash table to the bitmap, there might be
No, no, that is lossless. The hash table to bitmap compression is lossless as far as my purpose is concerned. I am not merging any buckets. Each bucket gets a bit, and that bit tells me if the count is greater than the threshold or lesser than the threshold, right. So, there is no loss. I am not combining buckets together when I generate the bitmap. It is a little subtle. So, when I asked did people understand, didn't understand, nobody said anything. So, I am just testing you now. So, unless you really understood what is happening, you won't be able to tell me why I need to check both bitmaps. It's not straightforward. It's not an easy answer. You have to think of a little bit. So, let's oops. Okay. Let's say that I pick a pair ij, right, which are both frequent, and then I check whether it hashes into a frequent bucket, and it turned out this bitmap gave me a 0. So, what will I do? I will not count that pair, correct. Now, come here, I take the same pair, I hash it to bitmap 2. It is a different hash function, right. It is going to collide with another set of pairs than it collided with in pass 1, right. The hash here that we had was a different hash, right, and the hash that I am using here is a different hash function. So, it could be potentially colliding with some other things. I did not even hash this pair, I did not count this pair in the pass 2, but now when I hash it, it might actually hash to a frequent bucket, because it is colliding, it actually colliding with a pair that is frequent under this hash function. So, it might hash to a bucket that shows up as frequent. So, I will add this to my candidate pair. Well, ironically, I have already eliminated it in phase 2 itself. In pass 2 itself, I eliminated this pair as being not frequent, but in pass 3, I might reinstate it as being a frequent pair, because it is now colliding with a different frequent pair. Okay, so that is a problem. So, I will check in, first I will check in bitmap 1. So, by checking in bitmap 1, I know whether I have actually counted this pair in pass 2 or not. Okay, you get that? So, if I have counted this pair in pass 2, then I will check whether the count happened to be in a frequent bucket. If it happened to be in a frequent bucket, then I add it to the items to be counted. Let's say that, wow, okay, that's, let's say I have this pair I and j, where both I and j are frequent, okay. So, I would have already counted this pair in some hash bucket here, right. Okay, now that comes here and that bitmap has a 0 in it. So, I will hash it here and I get a 0. So, what does it mean? That even though I and j are individually frequent, the pair ij is not likely to be frequent, because the bucket it hashed to has a count less than s. Perfect, right. Now, if I had hashed ij in pass 2, maybe it would have hashed to some bin, but I have not done that. I am not counting it at all, because I know that it is not frequent. So, I have not counted it, I have ignored it, I have ignored this pair ij. Now, I come back and get the pair ij in the third phase, in the third pass. Now, this bucket, right, is somewhere here, right. If I hash it, it will go to this bucket, and this bucket might have a 1 in it. Okay. If this bucket has a 1, in our modified algorithm, we will declare this ij to be a candidate frequent pair, and then we will start counting that ij here. So, we will make an entry for I j comma count and start counting that here. Right. Why could this be a 1? Because some other I prime j prime could also hash to this bucket here, right, and that was a frequent pair. So, I would have counted that and I would have made a 1 for that. But this ij, which I for sure did not include in my count, cannot have contributed to this frequent bucket, right. So, unless it hashes to a 1 here, I will not count the pair ij. So, it has to hash to a 1 in both the bitmaps. So, if it hashes to a 0 here and a 1 here, then I will not counted. Okay. Now it makes sense? All right, good. So this is basically what we have said here, right? Both I and j are frequent. The first hash function has to hash it to a bit, that's 1. The second hash function also hashes to a bit, to a bucket that has a 1, right? So that's basically what the multi-stage thing is. So the important part is the two hash functions have to be independent. So they have to cause different kinds of collisions, right? And we need to check both hashes on the third pass, right? So the explanation is exactly what I told you right now. Right? So remember, we said that we are going to use two hash functions that are independent in 2 stages, right? But you know what is the cost here again? We have increased the number of passes we do through the data. Is there a way to take advantage of the selection that we get by using 2 hash functions without increasing the number of passes through the data? We can, right? So what we do is the following. So when we do the first item count itself, right, we use 2 different hash functions, right? We have two different sets of buckets, right? And these are 2 independent hash functions, therefore the collisions would be different, right? Therefore, unless you hash to a frequent bucket under both hashes, right, you do not count the pair. Right, so you take a pair ij, right, and now if ij is truly frequent, right, ij is truly frequent, every bucket ij hashes to will have to show up as frequent, correct? If ij is truly frequent, every bucket ij hashes to will have to show up as frequent, right. So if when one hash it hashes to a frequent bucket, and in another hash it hashes to an infrequent bucket, that means that ij itself was not truly frequent. If ij is frequent, I has to be frequent, j has to be frequent. Okay. So what you can do is, in the very first pass itself, right, you can basically build 2 hash tables. Okay. Now the chance that an infrequent pair collides with, or rather hashes into a frequent bucket on both hashes is small, and then for the second pass you build 2 bitmaps just like you had earlier, right. So you can compress the first hash table into a bitmap, the second hash table into a bitmap, right, and that you can basically use now for filtering. So pass 2 will look like pass 3 of the previous algorithm. Basically you take an element. Now when I consider a pair ij from here, right, I know that both I and j are frequent, only then I am putting them together and making a pair, right. So when I am doing this ij, I know both I and j are frequent. Then what will I do? I will hash it into bitmap 1, I will hash it into bitmap 2, and in both if they are 1, then I will start a count for ij. I'll add an entry for the count, otherwise not. So the advantage here is we are doing it in 2 passes, right? We are doing it in 2 passes, and we are taking advantage of the hash idea, multi-hash idea, right? But what are we giving up? Always trade-offs involved in life, right? What are we giving up here? Memory. Somebody said something. I can't localize the voice. I just heard a voice. Again? Correctness. Yeah. So basically, what is affecting the correctness here is the fact that we have reduced the number of buckets per hash table. Right? We have reduced the number of buckets per hash table. So earlier we didn't, right? When we are doing the 3 pass algorithm, so the first pass had the full memory for the buckets, the second pass also had the full memory for the buckets. Now here we have taken whatever memory we had, we have halved it, right. Therefore, right, so it kind of doubles the average count, right. So it shouldn't come to a point where most of the buckets are going to have a count greater than s. because many pairs are hashing to the bucket, even though each pair is only contributing a small amount, right. We want to make sure that most buckets will not reach this count yes, right. If that case, right, then we can get a multi-stage benefit in just 2 passes, right. Of course, we can actually keep increasing the hash functions, right. So, what is the downside? So, in multi-stage, if you increase the number of hash functions, we are increasing the number of passes through the data. And multi-hash, if you increase the number of hash functions, buckets. So, therefore, more collisions are going to happen. But you are balancing that off by saying, okay, there are 3 different hash functions that I am going to use. The chance that an infrequent pair will get into a frequent bucket under all 3 hashes is small, right. But that is a challenge, right. You will have to trade off that, right. So, sometimes you can use more than one stage, you can use less. So, now we move on to 2 algorithms that are going to count frequent item sets in less than or equal to 2 passes, right, less than or equal to 2 passes. So, obviously, we are going to give up something. Correctness, okay, you kind of answered earlier for the thing, right. So, we are going to give up correctness, right. So, all of the things we looked at, PCY is essentially a more efficient way of organizing memory for a priori, right. So, it will take k passes to find frequent item sets of size k. So, now the question is, can we use fewer passes, right. So, we are going to look at 3 things. There is random sampling and SON. So, okay, you guys can pronounce the names, right. So, it is SON algorithm, and then Toivonen is another algorithm that, and these are all not really the names of the algorithm, right. They have just taken the names of the people who wrote the papers and then named the algorithms after them. So, the idea behind random sampling is very easy, right. So, what we do is you take a random sample of the baskets, right. So, in memory, right, just take as many baskets as you can fit into memory while leaving space for counts, okay. Now, because the amount of baskets is small enough that it can fit in main memory, right, you run your a priori or whatever algorithm that you want. You do not care if you are doing k passes through the data. Why? Because everything is in memory. So, k passes in memory is way faster than k passes in when you have to access the disk, right. But you also do a trick here. You reduce the support threshold. Suppose I needed yes was my original threshold and I have sampled 1/10 of the data, I set my support threshold as yes by 10. Or if I sample 1/100th of the data, I set my support threshold as yes by 100, right. And then you run your algorithm, then what you do? You run k passes of your algorithm. Are you done? No. So, the difference is when you take the random sample and you run a priori on it, what this a priori returns as the frequent item sets are your candidate item sets, right. What this version of a priori will return, because you run it on only 1/100th of the data with the 100th of the threshold agreed, right, but that does not guarantee that this will actually have the threshold yes in the full data. Right. Now, what you do is you count for all the item sets in one shot, all the item sets that you have as candidate item sets, you count in one shot on a second pass through the data. But this is a pass that will happen through the disk, the full data, not the sample data. Right. This way you can avoid false positives. Now, this is a way to avoid false positives. And you can, and there is no question of whether you are counting pairs or triplets or 4 tuples or 5 tuples, because you have done the full a priori, right. You have found out whatever is the 8 tuple, 9 tuple that is frequent, you have already found in this 1/100th of the sample. Now, you can have all of those frequent candidate item sets, right, in memory and just count as you go down, right. So, it is just done in one shot. So, basically 2 disk passes, right, you are done with this. So what is the price you are paying? False negatives, that things that were thrown away by your a priori algorithm as not being frequent in the sample will not be caught now. So, there is a chance that you will miss certain truly frequent item sets, but there will be no false positives because you are actually verifying this again on the full data. So, within 2 pass. If you do not care about false positives, you can be done in 1 pass. But remember, this is a cheating pass, you know, when I say 1 pass, it is about pass on the actual disk, right, not, so in memory we are doing many passes, but what is expensive is the disk pass, right, going and reading the data fully from the disk. So, we are doing only 1 pass on the disk, therefore, it can be looked at as a 1 pass algorithm. So, one way to minimize the false negatives, right, so things that we miss, that we do not count, is to actually, you know, set the threshold lower than just proportional to the sample. Suppose I have taken 1/100th of the sample data, right, I set the threshold to, instead of S by 100, I set it to S by 125, right. So, what will happen is I might catch some more false positives, but false positives are okay, right, because we can go back and do the full count and then eliminate that, right. But you are less likely to lose truly frequent item sets, okay. So, that is the random sampling idea, right. The SON basically tries to do this slightly better. Right. So, what the algorithm does, right. So, what the SON algorithm does is basically takes the randomness out of the random sampling idea that we talked about. Right. So, instead of sampling some random subset and running a priori on it, right, it samples a huge chunk in memory, right, however large a chunk will fit in memory, so that you still have space to maintain your counts, right. You sample a chunk into memory, run your a priori on it, get the counts, okay. Then remember which are all the frequent things, keep it aside. Sample another chunk, right, run your a priori on it, find all the frequent pairs, right, or whatever frequent tuples, pairs, any k tuple, right, and keep that aside. Right. Keep doing this until your entire data is read. Now, this constitutes 1 pass through the data, right, you have read the entire data. Even originally the sampling constituted 1 pass through the data, because you will be going through the data and randomly pulling out things and putting it into memory. Now, what you are doing, you are going through data, systematically taking chunks, putting it to memory, going back, then reading another chunk, putting it to memory, and so on and so forth. But still it constitutes 1 pass through the data, but the pass is taking a lot of time, right. You first read a chunk, run a priori on that chunk, because it is all done in memory, it will run very fast, okay, then go back and get the next chunk and so on and so forth. Now, here is a version of the monotonicity property that we had in a priori, right. An item set becomes a candidate if it is found to be frequent in at least one of the chunks that we read into the memory. So, I take the entire data set, I am reading chunks into the memory, right. So, remember, just like in the random sampling, my threshold has been lowered. So, in my random sampling, if I take 1/100th of a sample, I set my threshold at S by 100. Here, if my each chunk is 1/100th, then my threshold will be S by 100. Okay. So, now on the second pass, I look at all the candidate item sets and determine which are frequent in the entire database. Okay. So, the idea is this, right, an item set cannot be frequent in the entire database unless it was frequent in at least one of the chunks. If in every chunk it was not frequent, right, I have 100 chunks, and in every chunks it does not reach S by 100, then there is no way in the entire data it will reach S, correct. At least in one chunk it has to reach S by 100. That is the idea behind this algorithm. So, it does 2 passes still, right, but here the second pass is essential. So, it does 2 passes. So, now I look at every item set that was frequent at least in one of the bins, one of the batches that I processed, right? And then I'll count for only those, I'll count in the entire data. So no false positives, no false negatives. We really have lost nothing here. Sounds fishy, huh? Yeah. Yeah. Anyway, so maybe the downside is you have to learn to pronounce the authors' names. Only downside here, right? And even more amazing thing with SON is that you can actually run it in a distributed fashion. So I know that you guys didn't do any map reduce, but it lends itself very nicely to do this kind of distributed processing, right? So basically, as you are reading the data, right, you kind of send out each chunk to a different machine, right? Each chunk of the data you read goes to a different machine, and every machine is basically running the same algorithm. Every machine runs a priori in parallel, right? And then you take a union of all the frequent baskets, frequent item sets, each one of these machines discovered, right? And then you rerun. Now it's no longer distributed. You just run this on one machine, but actually you can do distributed counts also in a very efficient manner. And it turns out that so two sets of distributed distribution and gather, right? Distribute the data, gather, distribute the data, gather, and you are done. So it's becomes very efficient in this kind of distributed computing, right? So like I said, we didn't do MapReduce, and therefore I can't show you the MapReduce version of it. It's very okay. Well, actually, this is the last thing I'm going to talk about, but it's a little tricky thing, right? So the idea here is that we are now going to introduce an algorithm. One second. Right. So it's an algorithm that with a high chance will end in 2 passes, right? But it might take more than 2 passes. Might take more than 2 passes, but with a high chance it ends in 2 passes. So the idea is the following, right? You start with a random sample, right? Just like we talked about in the random sampling case, right? You sample 1% of the baskets and you set a threshold as S by 125, which is lower than the proportional threshold. The proportional threshold would have been S by 100. Remember, in the SON algorithm, you use the proportional threshold, it's fine. So if you take each chunk has 1% of the data, you use a threshold S by 100. You don't have to lower it any further. Use a threshold S by 100 is all good, right? But here you lower the threshold slightly, say S by 125, right? So find all the frequent item sets in the sample. Look, there is no K here, right? There is no pairs or anything. Just find all the frequent item sets in the sample by running your favorite algorithm multiple times, just like multiple passes, just like we talked about. Now, the candidate item sets that you are going to consider are all those item sets that are frequent in the sample that you have taken already, right? This is like in the randomized case, right? So all the ones that are frequent in the sample, and then we define something called the negative border of these item sets. So the negative border of these item sets, right, are sets such that the set itself is not frequent in the sample. The set itself is not frequent in the sample, but every one of its subset, immediate subset, is frequent in the sample. Right? Every one of its subset is fine. I don't have to qualify it by saying immediate subset, but every one of its immediate subset is frequent. Right? So what do I mean by that? So ABCD is not frequent, but ABC, BCD, ACD and ABD, all the 4 subsets that I can form are frequent. Right? So that's what I mean by the negative border. So ABCD will be in the negative border. So, the negative border could contain 3 tuples, could contain pairs, right. So, the negative border will contain a pair if suppose I have AB, both A and B are frequent in the sample, but AB is not frequent in the sample. So, AB will be in the negative border. Likewise, now we just gave an example of 4 elements, a 4 tuple that could be in the negative border and things like that. So, the idea is the following, right. So, see, it is highly unlikely that an element where none of its, some of its immediate subsets do not appear to be frequent in the sample will itself turn out to be frequent in the full data and not in the sample. So, that is the hypothesis here with the Toivonen algorithm. So, what you do in the next case, the pass 2 for count all the candidate item sets, right. Basically, the candidate item sets include the frequent item sets and the sets in the negative border, and for this you count on the entire data, right. Then if no item sets from the negative border turns out to be frequent, if no item set in the negative border turns out to be frequent in the real data, alright, we are done. Some of the candidate frequent item sets that turned out to be frequent in the sample could turn out to be not frequent in the real data, right. That is possible, but what we are hoping is everything that turned out to be frequent in the sample turns out to be frequent in the real data, right. But the negative border does not turn out to be frequent. So, if the negative border does not turn out to be frequent, thanks to the a priori property, nothing that contains a negative border can be frequent, right, and we have already checked everything that is below the negative border. So, we are done. So, we have not lost anything. So, no false positives, no false negatives, right. This is an additional layer of check over the randomized sampling thing that we did earlier. In randomized sampling, what we do? We just said, okay, I will set the threshold to S by 125, then I will do a second pass with all the candidates and I will stop, right. What the Toivonen's algorithm says is, no, you just add to this the negative border, the idea of the negative border, then if no item set from the negative border turns out to be frequent, then we can stop. What happens if something from the negative border turns out to be frequent? Now all bets are off. So, if something from the negative border turns out to be frequent, there is some chance that something larger than that also is frequent, right. So, we could potentially be missing a bunch of things. So, for example, AB turns out to be, remember I was telling you A is frequent, B is frequent, but AB was not frequent in the sample, and therefore, we would not have considered ABC as a candidate frequent item set, ABD as a candidate frequent item set, all of those things we would have ignored because AB is not frequent in the sample, right. But suppose AB turns out to be frequent in the entire data, now all those things that we have actually ignored earlier, right, now all of those we have to start considering. So, basically what you do then is you go back, you take a completely different sample of the data and then start your Toivonen's algorithm again, right. So, one way to avoid this happening is to make sure that your threshold that you set, right, instead of S by 125 maybe set it as S by 150 or something, right. What is the challenge in setting the threshold too low? If you set the threshold too high, there is a chance that you might miss truly frequent items. So, you want to lower the threshold, but if you set the threshold too low, you may generate too many candidate pairs or too many candidate item sets, and so when you are counting it in the second pass, the count table might not fit into memory. Then you will have to think of ways of compressing the count table and things like that. So, that is the trade off here, and so you choose your support threshold so that your negative border truly turns out to be the limiting condition, right. So, and then we stop and we can report. So, the nice thing about the last 3 algorithms we looked at, even though there is guarantees of correctness goes away, in SON it's like mind blowing, right. So, really there is nothing that you trade off with SON, especially if you are doing distributed SON. There is so much software infrastructure there available for you to implement them very efficiently. There are just tools out there, right. In fact, it turns out that the basic counting thing that we do in SON, right, is like hello world for MapReduce. So, when you are learning MapReduce, literally some of the things that you learned, right, is basically how to do counting in a distributed manner. That's the simplest thing that you can do. So it actually is a pretty powerful idea for doing frequent item sets. Anyway, so we are done. So